Hi there, this is Penelope, and this is a short video in the series of videos on introductory mechanics for the Level 4 Foundation course here at WellTech. We can divide physical quantities into two groups. We can divide them into scalars, and we can divide them into vectors. And the difference between these is that a scalar has a quantity, a size, but no direction, or the direction is irrelevant. Whereas a vector involves a quantity where the size is important and the direction. For example, here in scalars we might look at temperature, mass, time, distance, speed, I'm going to run out of space, voltage, energy, and for vectors we might look at force, displacement, velocity, and momentum. Now we're going to look here mainly at vectors, and a vector is drawn as a straight arrowed line, and it has a tail and it has a head. So it has a tail and it has a head, and the arrow points in the direction of the vector, and the length of the line represents the size or the magnitude. And you might represent it by that, or lots of squiggles on the top, or an arrow underneath, or an arrow on the top, or you might write it in bold. Textbooks usually write it in bold. Many vectors, many quantities in physics are vectors, and we need to be able to add them together or multiply them or divide them by scalars. We need to just briefly look at frames of reference. And this is a pair of directions at right angles to each other like that, similar to the ones that we use in maths. Now we might use points of the compass. We might use compass bearings, or we might use the vertical and the horizontal axes as we do in maths. Let's have a look at the points of a compass. Say we've got north, east, south and west. The north-south is at right angles to the east-west. And suppose we've got suppose this is a scale diagram. It's a bit tricky to do that here, but suppose it's a scale diagram and we want to draw a vector 32 degrees east of south. So we'd put 32 degrees in there. 32 degrees south of east. And we'd call this length 350 kilometres per hour, perhaps. So we'd have some sort of appropriate scale there to represent the 350. If we were going to talk about a compass bearing, as the military may talk about, then we'd have our bearings from north. So the same information as on the previous slide where it's 32 degrees south of east, we would draw this. So there's my 32 degrees in there, but now I'm going to draw it from there, and I would say that that was 122 degrees. Same length, 350 kilometres per hour. Now in maths we'd show it differently. We'd have on the axes the vertical component, the horizontal component, and not the same one, but we'd just have an angle from the horizontal and the appropriate length. So those are just different ways of representing a vector. We need to be able to multiply or divide them by a scalar. So suppose we've got a vector, this is some vertical component, and this is some horizontal component, and we've got a line that's representing 10 meters per second, and it's at 56 degrees. If we multiply that vector by, say, 5, then the new one is going to be the same angle, 56 degrees, so that's there, but it's going to be 5 times as long. So then we would say that was 50 kilometres an hour. You'd have some sort of appropriate scale so that my 10 metres and the 50 metres per second were on the same scale. We need to be able to add and or subtract. So we know in maths anyway what a plus b is. But here it means that vector b is added to vector a. So we've got a that way and b that way. What we do is we first up draw a, and then we join b so that the tail of b starts at the end of a, like that, and then the resultant diagram is a plus b. And some textbooks use a double arrow like that to show the resultant vector. And subtraction is the other way. So subtraction would be a plus negative b. More on that in a minute. Right, here we have an example of adding vectors. We've got a tourist couple, they travel 56 kilometres, I think that must mean 5.6. Oops, that doesn't actually make much sense. That's a long walk. Let's change that to 5 kilometres east. So they're walking in the north-south direction. They go 3 kilometres south, and then they go 6 kilometres north. And if you think about those as being in opposite directions, the resultant is 3 kilometres north. In the east-west direction, they walk 5 kilometres east and then 4 kilometres west, and then overall that gives them 1 kilometre east. Now we can draw that like that with a north up there. This is now they're going 3 kilometres north, they're going 1 kilometre east, and they're going some distance. If we just did a shortcut from where they started, we could find d and theta. The resultant vector is found by adding the two vectors and finding the length. So d, the distance, the length of d, is found by Pythagoras. It's just the square root of 3 squared plus 1 squared, which is the square root of 10, or approximately 3.2 kilometres. So that's how far they walked. But to find the angle, we remember from trigonometry that the tan of an angle is using the information that we've got, where it's opposite over adjacent. So in this case, it's 3 over 1, which is 3. Then we use our calculators to find theta, and theta is 72 degrees. So what we've got is that the tourists walked, in effect, or they ended up 3.2 kilometres and 72 degrees north of east. So around that way there. As I've already mentioned, subtraction is just going the opposite, but it does mean we need to think about what a negative vector is. A negative vector is one that just goes the other way. It's the same magnitude but going in the opposite direction. So we can subtract by adding the negative. So if we want to subtract b from a, we would say it was vector a plus the negative of b. And this is, if you're thinking about velocity, initial velocity and final velocity, and you want to find the change in velocity as being v final minus v initial, then we're going to have to subtract. So it would be the same as adding the opposite. So we've got VF, and then we need the opposite of VI, and there's our resultant there. Any vector can be broken down into two vectors at right angles to each other, and we talk about these as being the components of that first vector. Suppose we've got here a mathematical example where we've got 30 degrees and this is 10 newtons, and we need to find the two components. Now the vertical and the horizontal, so that's the vertical and that's the horizontal, we can find these by using trigonometry, and we should know that sine of 30 equals the opposite over hypotenuse. So that's the vertical component over, in this case, 10. We can do some rearranging so that we can find that the vertical component is 10 times sine 30, which is 5 newtons. So that's the vertical. And we can similarly say that the cosine of 30 is the adjacent. It's the adjacent over the hypotenuse. So that's the horizontal component over 10. Rearranging that, so we've got that the cosine of 30 times 10 will give us the horizontal component, and if we work that out on our calculators, it's that. The last thing I want to look at here is relative velocity, where suppose we've got a bus at 10 kilometers per hour and a little red car at 6 kilometers per hour. It depends on where you're sitting. If you're sitting in the bus, then it would seem like the car was going backwards at -4 kilometers an hour. If you're sitting in the car, it might appear that the bus is moving forwards at only 4 kilometers an hour. So if you're in the car, the relative velocity would have appeared to be 10 minus 6 equals 4. But if you're in the bus, it would be, so the relative velocity there would be 6 minus 10, which equals -4. So it would look like you were leaving the car behind.